My name is Martin Scheringer. I work in Switzerland and in the Czech Republic. I'm a scientist, and my field of research is chemical risk assessment. And in the last 10 years or so, I have also conducted research into the risks and the behavior and fate of nanoparticles. And that's also why I would like to share with you, as the first part of this lecture, 3 lessons we have learned from nanoparticle research, but that's research into engineered nanoparticles, not nanoplastics that are formed in the environment. Then, second, a few thoughts about and questions about nanoplastics, and then I will try to put the problem of nanoplastics into perspective in the last bit. So, the 3 lessons we have learned in the last 10, 15 years. First, nanoparticles are different from normal chemicals such as pesticides or food contact chemicals. They have different properties. They need to be measured in different ways. And that's very important because it means we cannot just apply the methods we know from normal chemicals to nanoparticles. Second, nanoparticles don't have a well-defined identity. They change over time a lot in the environment or within an organism. And the third lesson is studies of the behavior and the effects and properties of nanoparticles have to be designed very carefully, because we have seen in the last 10 years or more, many studies were not really designed appropriately, and they generated a lot of meaningless results, and a lot of time and money and energy and effort was wasted. A few words on each of these lessons. So number 1, nanoparticles are different from normal chemicals. As I said, they have properties that are different. For normal chemicals, we have properties such as solubility in water, or volatility, a tendency to volatilize, or what we call partition coefficients, and this is the ratio of two solubilities in water and in lipids. And these partition coefficients are very important because they describe the tendency of a chemical to go into water or blood or lipids. Nanoparticles don't have these properties. They don't dissolve in water or blood. They just kind of float around in a dispersion, as we call it. They don't have partition coefficients, but still many people try to measure and report partition coefficients for nanoparticles. And that's why we published this paper, The Road to Nowhere, Equilibrium Partition Coefficients for Nanoparticles, because it was frustrating to see again and again these meaningless papers. Nanoparticles behave differently. They aggregate, they stick to lots of other materials. They are often not stable. That's why they change over time, their shape and their form. And that's, as I said, the second lesson. So they do a lot of things when they are in the environment. There may be a pristine, original form of how they were made and used, but then once they enter the environment or they enter an organism, they change. You see different things that may happen. They may aggregate and form larger aggregates, and it may even lose the nanoscale. They may change chemically, they dissolve, or they undergo a chemical transformation. And they may also, and it's very important, they may change their surface, the coating. The surface is very important for nanoparticles because it's big, it's where the reactivity is, and they may lose the initial coating and they may acquire a new coating from all the materials that are present in the environment. On the right, you can see that they stick easily to other particles, to bigger particles that are present in the environment, and then that changes their behavior because they now are carried around, moved around with the bigger particles. So many things happen and change, and it's very dynamic, and it's very difficult to characterize and to identify what is the relevant nanoform of a nanoparticle that we have to actually risk assess. The third lesson was this one, that the studies are often or were carried out in a way that didn't generate meaningful results, and that's exactly because people didn't really know what the meaningful or what the relevant nanoform or nanoforms are, that they should have characterized and investigated. They didn't. So others could not really use the results because they didn't know what the results were made from. Or the methods that were used didn't really produce any meaningful outcomes because they were methods from normal chemicals. So that's why these results are so often fragmented and cannot be compared really and synthesized and aggregated. There are interesting review papers. If you're interested in this, you find very good overviews. There's one, I would just read one quote to you here from an important overview paper by Maynard and Aitken in Nature Nanotechnology. And it says, I have to look here and read, the nanotechnology safety research portfolio has become increasingly unbalanced over the past decade, with toxicology research far outstripping exposure-based research, and research into specific materials, silver or titanium dioxide, for example, has not always aligned well with likely potency or impact. So this means that people just investigated the same material again and again and again, although it was not really the most relevant material. And we looked into this, we discussed with colleagues, and often they say, yeah, we asked, why did you investigate this particular material? And they say, my boss told me so. And why did your boss tell you? Because the other groups also investigate that material. So it's a totally artificial bubble of research that has no connection with actual potency or impact. All these lessons, these three lessons, of course, also apply to nanoplastics, although nanoplastics are mostly not engineered particles that are made and used in products, but particles that are probably mostly formed in the environment. So we can go to the many questions we may have about nanoplastics. As I said, mostly they are not used in products. I was interested to hear that you mentioned that there are packaging that contain these polyacrylate nanoparticles. I would like to learn about that. But mostly they may be formed in the environment by weathering, by breakup of larger particles. Then the questions, of course, are many. What are the rates of this process? How many of these particles are generated? What are their properties in fate? How do they age and change over time? And again, what's the human exposure? Is there any? What's the pathway? Seafood? How many of these particles is it that we may take up? And then also, what are the possible effects? For many of these questions, you would still have to develop the methods. So that's a big scientific task that we may be interested in, and we may get the funding for it, and then we will be busy for many years with it. But that's kind of our world and our part of the problem. And it has been started already. So I contacted a colleague of mine in our field, that's Nathalie Tufenki at McGill University in Montreal. And Nathalie has done this kind of experiment where they took microplastic particles and then put UV light on them, UVA light, and they could see in the laboratory that the microparticles broke up and formed many, many smaller nanoscale particles in the lab. That's unpublished work, but there will be a paper soon that comes out from the Tufenki team at McGill. Nathalie also and her team, they also work on methods for detection and quantification of nanoparticles in the environment, in complex matrices, in complex samples, for example, from wastewater treatment plants. And this is a nice review paper they just published this year in the Accounts of Chemical Research. And here I also want to read to you just one quote. What they say here is, a common theme in our account, or this is this paper, the account, is that new techniques are required to answer key questions in the field of microplastic and nanoplastic research. So again, what I said at the beginning, we have to find the appropriate methods before we can say anything solid about these materials. Same, so this is now methods for identification, detection, and quantification. Same question or same point also applies to toxicity testing. We have heard already several points by Martin and Tamara. So one thing is, of course, at any size, if there's enough of the plastic, it has this physical obstruction, the physical toxicity that you mentioned, Martin. You can kill any animal organism by a sufficiently high number of particles that just kind of block the gills or the mouth or the intestines, or that kind of just strangle the organism and do all these kind of physical obstruction. That's independent of the size. The nano size is tricky because, as Tamara also said, of course, they may enter the cells at the nanoscale, the particles. Again, there has been a lot of research into this, also from the field of ultra-fine particle research, where people were investigating the behavior of the particles in the lung. So there's a lot of research into how these particles then may enter the systemic circulation in the body after penetration and entering the body. So also for toxicity testing, again, we have to find out what are the forms in which these particles may be present, and that need to be risk assessed if that's a relevant point. And also what are the relevant doses, because again, if we go too high in the doses, we always find an effect just by the physical presence of the materials that kind of block the fundamental processes of the organism. So we may start here a huge program of research into all of these questions. And again, that's perhaps what we, the three of us, may like to do in the future. But I would like to ask here the question of, is this feasible? Is this desirable, really? And to answer this question now at the end, I would like to take a step back and look at the bigger picture here. And I would like to start from the biggest part of the big picture. And the biggest part of the big picture is macroplastic. We all know that. Macroplastic has caused a bloodbath among marine wildlife. And it's a disaster, it's terrible, and it's something we have to act on more or less immediately. And without any more research, I would say. Then we may move on from macro to micro, because we have the breakup and weathering and formation of smaller particles. And also that is a problem. We also have a concern here because there are so many, and they may also affect many organisms just by their sheer presence, the microplastic particles. If we keep going, we go to the nanoscale, and here I would say I'm not sure exactly how big the concern actually is, and we may have to first conduct a lot of research to find out what really needs to be done here. On the other hand, we have our topic here, food contact chemicals. And we don't even know if or to what extent food contact chemicals overlap with nanoplastics. And I think that's why nanoplastic is perhaps not the most appropriate angle to look at the problem. Because it's just the far end of the distribution of the plastic problem as such. So in a way, we have to do a lot of work just practically to stop plastic pollution. That's one thing. And on the other hand, we also have to work on reducing the exposure to food contact chemicals. And if it's shown in this way, the two things look a bit disconnected. But of course, there's a lot of overlap. So if we turn this around, it looks like this. And there is a lot of overlap between the problem of food contact chemical exposure and use of plastic in food packaging. And that's where we have a synergy between these two areas, and we need to do practical work to reduce the use of plastic in food packaging, because that helps in both directions. Whereas nanoplastic then is at the other end of the spectrum, and I think, as I said, nanoplastic is probably interesting and important as a topic for research, but I wouldn't say that nanoplastic right now is a useful topic for advocacy work. And with that, I would like to thank my colleagues, Natalie, Miriam, Thomas, and Ralph, and I thank you for your attention.